So in this second lecture of the course today, we'll be turning our attention to the regression problem in machine learning. So you might recall from last lecture that we addressed the classification problem. Hopefully the picture you have in your head is something like that shown here, where our data is organized into two distinct blobs, each of which has a distinct label. In this case, we could see that a line would separate the two classes. One such class would be above the line, and one would be below. And so we encountered the perceptron algorithm for that learned a particular parametrization of this line, specifically a separating hyperplane, to enable binary classification. A common characteristic of the output labels we sought to predict is that they were categorical. And so that is that they belong to elements in a set that took on integer values. So for example, in this plot here, the output variable y takes on two values, which are visualized as either dark blue or yellow. Among other things, this allowed us to definitively know when a mistake was made, and we could update the weights accordingly. We also saw how to generalize this to the multi-class setting. However, very often the outputs that we want to predict are actually continuous values. So that is, they lie in the space of real numbers. So for example, in this plot here, y now takes on a color over a spectrum. It's not constrained to be binary. We can discern some relation to the underlying features of the data, x1 and x2, and that the darker colors indicating lower negative values of y are predominantly in the lower left, while the brighter colors indicating large or positive values of y are predominantly in the top right here. And so predicting continuous valued output given features of data is known as the regression problem in machine learning. The perceptron algorithm, as we learned it, at least as we learned it, does not apply as it's meant for classification tasks. But more importantly, we can also see that the idea of a mistake or error, as we saw on Tuesday, isn't meaningful in this context anymore. For example, suppose someone gave us a model that could predict the output given the features. How would we evaluate it? We couldn't rely on this idea of mistakes our algorithm makes anymore. As the output variable can take on a value with arbitrary precision, our predictions would never match exactly. Instead, the mistakes that get made now also lie on a spectrum. Our predictions can be either a little bit wrong or very wrong. And so in this lecture, we'll be attending to how we can solve the regression problem. And the key idea will be to expand on our idea of mistakes the model makes to this more general concept of loss, which captures the extent to which our model deviates from ideal behavior. Crucially, ideal behavior is a fuzzy concept. We'll see that this generalization will mean that for any given problem, there's no one correct loss. And in fact, as a machine learning practitioner, the loss is something that you must choose or design, and actually might require some iteration. Once the loss function is designed, however, the goal is to find the parameters that minimize it. And whether you have an easy time or a hard time in this last step has a lot to do with how you define loss to begin with. So by the end of this lecture, the goal is to have demystified those steps a little bit. The aim is to get us to a place where we can go and write code to solve a simple regression problem numerically given a data set. I also want us to be able to talk about loss intelligently and understand the mathematical principles underlying this concept to be able to design them when you need to do. Finally, you'll be able to use best practices in reporting your model evaluation results and managing the design process, including the tricky case of when you had to follow an iterative design process. So to get us to that point, we'll be focusing on three key questions. We'll first focus on figuring out just the basic steps we need to take to solve the regression problem by looking at a simple example. We'll then dig a bit deeper into the loss function specification step in particular, and think about what we should consider in that design process. Finally, we'll address the practical issues that often come up when the design process is iterative, And as usual, we'll close out with a summary. All right, so turning our attention to the first question. What's just the basic process for solving regression? So it always helps to start with just the simplest possible problem we can imagine. So this scatter plot depicts the observations of a data set with one feature. The one feature is on the horizontal axis. The dependent variable is on the vertical axis. And each point represents one observation. The setup of the regression problem, then, is that we're given a training data set of k observations, each composed of an independent variable x and an outcome y. As in the classification problem, the independent variable x is in general a vector, so it lies in the space of real numbers of dimensionality d, for some d. Unlike the classification problem, though, the outcome now belongs to the set of real numbers. And so for this data set, we can recognize that d is 1, as our feature vectors have one element. The goal then is to learn a function h that will map from the space of real numbers with dimensionality d to the real number line in a way that best approximates the relationship between the variables. And so with this function, the idea is that this will allow us to predict the outcome y given a particular feature vector x. And we're being intentionally vague about what it means to best approximate the function right now, but we'll get more specific about that in the next few slides. And so you also might recall that in the last lecture, we had a choice in how we could approach the classification problem. Specifically, these were the statistical or batch learning setting and the online learning setting. And we encountered the perceptron algorithm, which we recognize as addressing the online learning problem, as the data was presented to the learner in a streaming fashion, that is one sample at a time. It had to predict the label y before knowing what the correct label was, and we were interested in making as few mistakes as possible. In batch learning, as the name suggests, we now have access to a batch of data, actually 2 batches of data, a training data set and a testing data set. We're most interested in the performance on the testing data set, but the training data set provides a means to learn the model. And the most widely used algorithms for solving this problem involve making statistical assumptions about these 2 sets, specifically that they're drawn IID, independently and identically distributed from the same distribution P. And so the problem that we've been tasked with today is actually we've been given a batch of data and the task of approximating a function from it all at once. So we'll be working in the batch learning setting today. So here I've got the batch learning problem we had for classification in the top right, and the data pictured on the left for reference. And so how can we reformulate the batch learning problem that we saw last time to be meaningful for regression? Well, one thing we need to do is tweak our goal a little bit from that we had in classification, where we wanted to learn a function h that would map to an output that would take on values of either plus or minus 1. Now we want to learn a function h where the output can take on continuous values. That is, it lies on the real number line. And of course, we don't just want to learn any function that maps to the real number line. We need it to do something useful. And so for the classification problem, we took it as our goal to learn a function that maximized the probability that our predicted labels would match the true labels. And so here we can see a second issue for the regression problem, in that this test of equivalence is no longer meaningful. For example, if the actual output was this black dot here, each of these pink dots would technically be wrong. Each of these pink dots representing 2 possible predicted values. But clearly, one of these is a lot more preferable than another. So one way around this is to specify some loss function, which we'll denote as L subscript W of x and y. And so this function, which we only need to have in general terms right now, is a function of the parameters of our model W, input x and output y. And this is going to define the extent to which our model deviates from behavior that we would consider ideal. And so then we can change our goal to be more specifically that of making the expectation of this loss, denoted by the capital E, to be small. All right, so are we done? Well, not quite. You might notice that we want to minimize the expectation of this loss for xy drawn for some distribution that we call P. However, this distribution is unknown to us. What we can do instead, though, is something called empirical risk minimization, or ERM. And this refers to minimizing the loss based on the data we do have. And so to do this, we sum over the losses associated with individual points, and then divide by the number of samples we have and take the average. And so we're interested in the parameters W that minimize this loss. And so what this means is that we perform an argument operation on the expected loss to give us back the parameters that minimizes the expression. And so why does this work? Well, by the law of large numbers, in the infinite limit, this sum will converge to the expected loss for the actual distribution, even though we don't know what that is. Okay, so putting this all together, we can now rigorously state our goal for the regression problem as given a training data set that is IID drawn from some unknown distribution P and a loss function, also W of X and Y. The goal is to find the parameters W that minimize the average loss for the training data set we've been given. Okay, so now that we've established the setup, we can focus on specifying the loss function itself. So this is where, as a practitioner, you actually have some freedom. The loss function is something that you at least choose and might even need to design. So this means getting clear about what ideal behavior would look like, such that you can quantify deviations of your model from that ideal. So how can we do that? Well, one thing we know for sure is that we want the model's predictions to match the true values as closely as possible. So in this case, we would define the loss function. We could be totally reasonable to define the loss function as just the difference between the true and predicted outputs, and then square it to make sure that over and underestimations are penalized equally, as shown here. We could then interpret the expected loss as the average of squared residuals, gamma, where the residuals themselves are the difference between the predicted and actual outputs. Example. And so finally, we need to select a model or the hypothesis class. And so in this simple example, we could intuit that learning a linear function of the features would enable us to make reasonable predictions about the output. And so this would amount to drawing a line through the points that gives the best fit. And the dot product between this parameter vector and the padded feature vector is known as the dot product between the padded feature vector and the parameter vector is known as the linear regression predictor in the machine learning literature. And the sum of square differences from that and the true output is our expected loss. Okay, so we want to find the parameters that minimize that loss. But how can we do that? Well, one thing we technically could do, I'm not saying this is a good idea, but we could do it. It's just a brute force search over the parameter space. Perhaps if you weren't taking this course, maybe you'd need to resort to these methods. And so what this involves is that we would just try out a bunch of different parameters and then compute the loss on our data set at each point, at each combination that we tried. And so if we were to do that, we would see something like this. So this image is a heat map over the parameter space. The horizontal axis is the slope of the fitted line, M, and the vertical axis is the intercept, B, for our linear predictor. The color then represents the loss for any particular choice of parameters. The dark colors is low loss, and the bright colors is high loss. And so we can see that the loss over the parameter space is not random. It has some structure. Specifically, there's a region with very low loss, and then we move into regions of higher loss as we move away from it in any direction. So this reveals that within the range of parameter values we explored, there seems to be a minimum, a choice of parameters that minimizes the loss. Another way to plot this is as a surface plot. So this is the same data we saw in the last slide, but now the loss is also represented by the height of this 3D plot. I also transformed the loss on a logarithmic scale to make a few characteristics more obvious. But now we can clearly see that the loss function surface exhibits a basin in parameter space, outside of which the loss is high. There seems to be a single minimum. And so this perspective also reveals something else to us. And so as we head towards that basin, to where we're interested, the rate at which the loss changes decreases, and then eventually has to change sign in order to get to the other side. And so we know that right at the point where it changes sign, in the middle of the basin that we're interested in, we know that the rate of change would actually be 0. So yeah, if you've heard of the term gradient in the context of machine learning, this is what we're referring to. At least in all the cases I've seen, it refers to the rate of change of loss with respect to the parameters. So if we could find a way to compute instead the gradient of the loss, then we should be able to more directly find out how to minimize the function than doing a brute force search over the parameter space. And so in order to do that, we'll need to make use of some calculus. So before we move forward, we'll stop to review some of the notation and manipulations. So the first is the derivative. So if you have a scalar valued function f of one variable, then the derivative of that function will also be scalar valued. An example of this is if our function was x squared plus 3x plus 5, then the derivative would be 2x plus 3. The gradient then is a generalization of the derivative for functions of vectors. This is denoted by this upside down triangle operator called nabla or del. So now if we have a scalar valued function of d variables, we now have to get more precise about what the derivative means, because we can take the derivative with respect to any one of them. We call the partial derivative, denoted by these delta symbols, the derivative of the function with respect to one variable. Taking the gradient of such a function means to compute a vector where each element is the partial derivative of one of the variables. So for example, if the function was a linear combination of variables, 2x1 plus 3x2 plus 5x3, then the gradient of the function would be 2, 3, 5. The gradient will be used extensively in this course, and it'll come up again in a big way when we turn our attention to neural networks. We'll also be using something called the Hessian. So this builds on our idea of the gradient, but produces a matrix containing combinations of partial derivatives. So it's a matrix of second partial derivatives. So what this means is that for any element ij in the matrix, we compute the partial derivative of the function with respect to feature I, and then with respect to feature j. This is an example function and its associated Hessian. I won't be walking through this, but could be a good exercise to try to prove that for yourself. So those ideas of gradients are pretty abstract, but they actually relate to this empirical problem that we have. To see how, we'll just need to represent our loss a little differently. Specifically, if we stack our padded feature vectors xi into a matrix, and we call that A, where A is size n by 1, and n is the number of observations. And then similarly, stack the output values y into an n by 1 matrix. We can write the total loss in another way, which is the squared L2 norm of the dot product between A and the parameter vector W less our output vector. And it's this matrix, it's this representation of loss that will allow us to compute the gradient. So we want to compute the gradient of the loss, meaning we want to compute the gradient of the L2 norm of this AW minus C inside the brackets here. So we can expand this part inside the brackets, and as we're squaring, this is the same as the factor multiplied by itself. And so now that we're working with matrices and vectors, we just have to transpose the first to make sure that the dimensions line up. Then we can evaluate the product using a matrix generalization of the FOIL identity to get this third line here. And so once we've done that, we're ready to take the gradient with respect to the parameters. We can see that this the last term, ZTZ, gets dropped because it has no effect on the rate of change with respect to W. The middle term becomes 2A transpose C. And then for the first term, because it involves W transpose W, this is essentially an element-wise squaring operation. So you just have to bring the 2 down and decrement the power on W. And so once we do that, we can actually evaluate the gradient of the loss for any particular choice of parameters. This would show us how the loss is changing at any point of interest. And we'd be able to overlay arrows like those depicted here, which show us how the loss function is changing at any point. Importantly, we can also find out where the gradient is 0. So to do that, we set it to 0, we've done in this next part, and then simply solve for a W. So now we can bring one of the terms onto the right-hand side, and then get rid of the 2's because they appear on both sides. And then to isolate the parameters W, we simply need to compute the inverse of A transpose A, and then multiply that by both sides. And so this gives us the final expression for the parameters where the gradient is 0. And so we can go and check that against our brute force search, which we denoted by this silver X here. And we can see that it actually it got pretty close using this closed form expression. So in the brute force, I sampled in a pretty coarse manner over this space. So we wouldn't expect them to match exactly. But I would expect the closed form expression to be more accurate than the brute force search. So yeah, I use that method a lot in my day-to-day. It's baked into the libraries that I take for granted, but there are some things to keep in mind in practice. First, the matrix A transpose A might not actually be invertible. This can happen when there is a multicollinearity among the features or when the number of observations is insufficient compared to the number of features. Another problem is that calculating A transpose A and its inverse can be computationally expensive, especially for large data sets with many features. The complexity increases with the size of the matrix, making it inefficient for high-dimensional data. And so there are some ways around this. We'll discuss that in a few weeks' time. A third problem arises when A transpose A is ill-conditioned. So this means that a small change in the coefficients results in a large change in the solution. And so this issue is problematic when solving systems where round-off errors occur. Like if you're dealing with the floating point, a fixed floating point precision values on a computer, like the NumPy library does. Direct methods like Gaussian elimination can be used to solve the linear system without explicitly inverting the matrix. So that's another way to do it. Yeah, so to recap so far, we've now stepped through the basic process of regression by solving a simple problem. We first positioned ourselves within a particular learning setting, specifically statistical or batch learning, and then defined a loss function using empirical risk minimization. We then defined a hypothesis class, specifically this class of linear functions, which can be rewritten using the padding notation. We then also compared the brute force search and the analytical methods of minimizing the gradient of the loss given the function, given the model, and hopefully convinced ourselves that the gradient provides an extremely useful source of information and definitely a more computationally efficient way to minimize than the brute force search. But now we need to focus a bit more on the leveraging gradient because it turns out that the loss function we choose determines whether or not we actually can use this trick to minimize the expression. The gradient isn't always so friendly. So this brings us to the next part of the lecture, which will focus more on loss function design. There's a few considerations here, but the one we'll focus on first is trying to design the loss such that we have an easier time trying to find the optimal solution. So to explain more what I mean here, here are sketches of two hypothetical loss functions involving one parameter. The one on the left is representative of the situation we had before, where it's got this nice smooth bowl shape, and we can identify a single minimum. So there's a single point where the gradient is 0. There's a clear global minimum in this function. Things are a bit more complicated for the function on the right. We can also identify a global minimum, but there's two other little dips that we can call local minimum. And so the problem is that each of these 3 points would have a gradient of 0, but they wouldn't necessarily, they wouldn't give us the optimal solution. So the key property that we use to distinguish between these two functions is convexity. And specifically, we would call the function on the left convex, while the function on the right is non-convex. And so what is convexity? Well, convexity is defined as those functions that satisfy Jensen's inequality, which is stated in this equation on the left. And so what this says is that if we were to interpolate between any two given points, x1 and x2, using a sliding parameter lambda, where lambda can be on the interval of 0 and 1, the function of that interpolation would be less than or equal to the interpolation of the function of the points. So this is easiest to understand geometrically. And so what it means is that the curve itself, the function of an interpolation between any 2 points, is always below the secant line that interpolates between f of x1 and f of x2. That is the pink line here. Another sufficient condition for convexity is based on their second derivative. Specifically, for a twice differentiable function of one variable, it is convex if and only if its second derivative is greater than or equal to 0 for all points in its domain. So for example, if we had a function of one variable, say x squared, like this bluish-green line here, then its first derivative would be 2x in yellow. And then its second derivative would be 2, which is positive for all x. This is actually an example of a strictly convex function, as it's not only greater than or equal to 0 for all x, but also satisfies the stricter condition of being greater than 0 for all x. For higher dimensional twice differentiable functions mapping from Rd to the real number line, R, such functions are convex if and only if it's Hessian. The matrix of second partial derivatives is something called positive semi-definite, or PSD. Positive semi-definiteness, in turn, is a property of a matrix. It's denoted by this curly inequality symbol here. And so it's analogous to describing a scalar as non-negative, but applied to matrices. Specifically, we say a matrix of shape d by d is positive semi-definite if and only if for all v in Rd, the condition v transpose mv is greater than or equal to 0. And so putting all this together, if the Hessian matrix of a twice differentiable function f is positive semi-definite everyone in its domain, then f is convex. And so why does convexity matter? Well, the rub really lies in Fermat's condition, which relates the gradient to the position of local extrema. Specifically, if x is a local extremum of f, then the gradient of f of x is 0. So yeah, this isn't that surprising. We could kind of tell that already. But if we know that if the function f is convex, then the converse of Fermat's condition is also true. And so if the gradient of f of x is 0 for some x, then x is a global extremum. So if f of x is convex, we can be assured that where its gradient is 0 is the extremum. And so for optimization problems, that means that if a function is convex, we can be assured that there is a single global optimum. And so with this definition of convexity in mind, we can now return to the least squares loss that we used earlier to check that it was in fact convex, and we didn't just somehow get lucky. So we had already looked at the gradient, but now we can look at the Hessian, the matrix of second partial derivatives, as it gives us a direct link to the properties of convexity. So the Hessian is this third line here, the 2A transpose A. And so plugging the Hessian into the definition of positive semi-definite matrices we saw earlier, we can see that this is equivalent to writing 2 times the squared norm of the product AV. And this is guaranteed to be greater than or equal to 0 for all phi. So ATA, A transpose A, is positive semi-definite. And so as the Hessian is positive semi-definite, we can conclude that the loss is convex, and therefore importantly, when its gradient is 0, we found a global extremum of the function. And so just to drive home how important this idea of convexity is in the field, and then it's not just some esoteric academic exercise, I just wanted to point you to a recent-ish paper published in NeurIPS, where the authors worked out a way to visualize the loss landscape of deep neural networks. We'll get into neural networks more in October, but the method they developed shed some serious light on just how non-convex neural networks can be, or the loss functions associated with neural networks can be. So for example, with this image on the left here, we can see that there is a global minimum, but the surface is rough and has a lot of little dimples punched into it. And so each of those little dimples is a minimum unto itself. And so the authors also played around with how the architecture of the network, specifically something called skipped connections, which I won't get into, what the architecture of the network has on the nature of this surface. And so with that change, this loss function surface got a lot smoother. It's still not convex, not perfectly convex, as there's this ridge in the back here, but it went a long way towards making this problem much easier to solve. So what I hope to convey here is that convexity is a key property you would want to check and try to design for in your loss functions. Basically, if it's a convex optimization problem, your life's going to be easy, or a little bit easier. But there's other things as well. And so specifically, these relate more to practical issues like numerical stability and generalization. So an important thing to keep in mind in optimization is that it'll do exactly what you asked it to do, minimize the loss. But this naive objective has some serious problems. Specifically, it can cause some weights to become very large. That is, the loss function is not numerically stable. It can be very sensitive to small changes in the data. And so this is a problem for the ability of the model to generalize. So one strategy to deal with this problem is something called ridge regression or Tikhonov regression. The objective is shown here. And yeah, we want to minimize over all of this. The first term represents the squared error between the predicted outputs and the actual outputs. This is what we had as the loss function before. And the second term we call the regularization term. It adds the squared magnitude of the weights to the loss function. And so the effect of the regularization term is to penalize large weights by adding their squared values to the overall loss. This effectively shrinks large coefficients, preventing any one feature from dominating the model. This variable lambda controls the strength of this penalty, and it's something called a hyperparameter. That is a parameter that's not trained or optimized, but that ultimately influences the ultimate learned model. A larger model results in more regularization, shrinking the weights more aggressively. And so the effect this has is that by discouraging large weights, ridge regression stabilizes the solution. And also reducing the magnitude of the coefficients helps the model avoid overfitting to the training data, which enhances its ability to generalize to unseen data. Without regularization, the solution might give disproportionately large weights to some features, which would lead to unstable models. And so while ridge regression penalizes large weights to stabilize them, something called L1 or lasso regression will drive some weights to zero. Lasso stands for least absolute shrinkage and selection operator, and it actually wears two hats. It provides regularization and also variable selection. The objective function for lasso is defined here. It's similar to ridge regression, but the last term we call it L1 penalty, which is the absolute values of the weights. And so in contrast to the L2 penalty, the L1 penalty encourages some coefficients to become exactly zero, effectively removing those features from the model. And so we say that there's a selective shrinkage, leading to a sparse model where only the most significant features are retained. As lambda increases, more weights are driven to zero. So this makes lasso particularly useful if you're dealing with something like high dimensional data where feature selection is crucial. So you can kind of think of lasso as kind of built-in feature selection method because it automatically ignores irrelevant features. And so this actually at once enhances both its interpretability and also reduces complexity. Of course, if lambda is too high, it might exclude important features, which isn't a phenomenon called underfitting. So therefore, a careful tuning of lambda is essential to balance model simplicity and predictive performance. So we've seen how crucial regularization is, but now we have a new problem. That hyperparameter lambda is something we have to pick, something that happens outside of the training process. So we almost need a kind of meta training process to develop the model. So we'll now move on to cover best practices there. So I guess before we get into this, it might help to take a little step back to refresh on the batch learning condition. So at the beginning of this lecture, I said that the batch learning problem, we have a batch of data, but specifically two batches of data. So I have a training data set and then a testing data set. And so the correct way to make use of these two sets is we first use the training data set to minimize the loss and estimate the parameters of our model. And then once we have those parameters estimated, we then examine the model's ability to generalize to data that it hasn't seen before with the testing data set, to see how accurate its predictions can be based on stuff it hasn't seen before. And so the accuracy on the testing data set is actually what we're interested in. And so if this is how you're using your training and testing data sets, this is exactly the right way to do things. But where you can get into trouble is if, for example, you went through this process from left to right, and you found out that you just did absolutely terrible on your testing data set. The temptation is to try to go back to the model to make some changes and then retrain your model on the training data set and then see how you did on the testing data set. And then you might make a few more changes in your model and retrain and then test again. And so that's the temptation, is to just try to improve your performance on the testing data sets. But there's a risk in this process, is that you can actually overfit to the testing data set. Um, Specifically, you run the risk of losing claims about your ability to generalize to new data, which is really what the testing data set is for. So yeah, if you're using your training and testing data set adaptively, then that's a big concern. So what can you do? Well, you can introduce something called a validation data set. So within the block of data that you had, now you partition that into three sets. And so what this means here is that using your training data set, you come up with several different versions of your model, each of which uses a different combination of hyperparameters. So in the regression example, that would mean, in the ridge regression example, or in the lasso regression example, that would mean you would have a model with a lambda of 1, a model with a lambda of 0.1, maybe a lambda of 10, and so on and so forth. And then you use your validation data set to select perhaps the best performing one, the best performing model. And then you still want to evaluate that, I guess, tuned model on the testing data set to see how well it can generalize to data that it hasn't seen before. But in some cases, you might not have a lot of data to work with. You might have a small data set, and you might not want to have to set aside data just for the purposes of validation. And so what can you do in this case if you don't have a lot of data and you can't afford to set aside? So in this case, you can do something called cross-validation. And what this is that you have a training data set and you partition it into k subsets, where k is some number like 5 or 10. And so here I've partitioned it into 5 sets. And so what you do is that you train on, say, 4 out of 5, and then you use the last one to validate your data. And then you do this process again, but the next time you select a different partition to use as the validation set. So you train on everything else, and then you validate on that one, and so on and so forth until every single partition has its turn as part of the validation set. And so in algorithm pseudocode, so you'd have a data set, this here, and then you input a number of folds, the number of folds, which is the k parameter, and it'll return the optimal hyperparameter lambda. And so how you do this is you set up a nested for loop. In the outer for loop, you loop over different values of lambda. And then in the inner loop, you loop over the partitions k. So like I said, you get your fitted parameters omega for a particular choice of lambda, and you train on the partitions of the data set D that are not I, so everything but partition I. And then you calculate your performance, or you evaluate your model performance as some accuracy measure on the partition I. And so once you've looped over all partitions for a particular value of lambda, you're in a position to calculate the average performance for that choice of lambda. And so once you've looped over all values of lambda, you can figure out which lambda actually performed the best. Okay, so those were some of the best practices for dealing with iterative model development. Okay, so I'm hoping by this point you now feel confident to go and actually write some code to solve the simple linear regression problem numerically given the data set. I'm hoping that you can now characterize and design loss functions of your own using, reference to the correct terminology as well as the sound mathematical principles like convexity, ridge, lasso regression that we covered earlier. And you're also a little bit more confident to evaluate your model